Good afternoon, all of you. In this chapter, States of Matter, initially we had told that we need to study two states of matter, which are the liquid state and the gaseous state. Till yesterday, we completed one state of matter, which is the gaseous state. So today, we are moving on to the next state, which is the liquid state. We all know about liquid state, how the intermolecular forces are and how the physical properties are. So we will have a brief introduction about liquid state. So the term fluid is used for either liquid or gas to recognize its continuity. Both the states, liquid state and gaseous state, is termed as fluid because they flow or they are continuous. So thus a liquid can be viewed as a very dense gas. So that's a hypothetical concept. A liquid can be seen as a very dense gas. If we increase the density of gas or if increase the number of molecules present in the gas, then it becomes a liquid. And both of them together they are known as fluids as they flow. So intermolecular forces are stronger in liquid state than that of gaseous state. All these are non-facts. So under normal conditions, liquids are more denser than gases. And in this figure only, if we consider a particular area, in a particular area, number of particles present in liquids will be more than that of gases. So we can tell liquids are more dense than that of gases. We do have some properties of liquid state to study, which are the vapor phase, surface tension and viscosity. All these three are some properties of our liquids. So initially we will study about the vapor pressure. So what is vapor pressure? So here we have taken a container with which we have filled with a liquid and it is connected to a vacuum pump. So this vacuum pump is connected so that to remove excess gas present in this area. So the vacuum pump sucks out the gas which is present excess than the liquid. So after vacuum pump does its process, we do have just the liquid inside the container. So as we know, which we have studied in the kinetic molecular theory also, liquids are also moving. So liquids in the particles are also moving. And when they move, they collide with each other, they can lose energy, they gain energy, etc. So some particles in the surface of this liquid gets more energy and they escape from the surface as in the form of vapors. So from the surface, some molecules or some particles of the liquid are escaping, gaining some energy and they stay as vapor. So liquid is converted to vapor in very little amount. So vaporization is a common process which we all have seen. We dry our clothes with the same process, right? So vaporization is a common process which we do at our home also. So there what happens is from the surface, due to increase in the energy, some molecules or particles escape and they stay inside the container if it is kept inside a container. So now what happens is these particles also start moving and they hit with the walls of the container and with the surface of the liquid. So when that happens, some amount of pressure is being induced inside the container and that pressure is known as the vapor pressure. So the pressure applied by these moving vapors on this liquid state and even the walls of the container is known as the vapor pressure. After some time, it becomes a constant or the pressure becomes constant. So an equilibrium is established between the liquid phase and the vapor phase. Why? Because so as they are moving, we told they collide to each other also and they lose energy. So some of them will lose their energy and they will not be capable of staying in the vapor phase. So they will come back and join with the liquid phase again. And that happens, there is an equilibrium between these two states. So some amount of liquid is being converted to gaseous state from the surface and some amount of gas by hitting to each other they lose energy and come back to the liquid state. So this process keeps an equilibrium between these two. So this stage is known as the equilibrium vapor pressure or saturated vapor pressure. So as this liquid and gaseous forms are in equilibrium, this stage is known as equilibrium vapor pressure or saturated vapor pressure. And what happens when we apply a bit of temperature to it? So when temperature is provided to this system, all the molecules in the vapor phase and even the liquid phase will have some amount of energy extra. So we are providing energy or external energy. So all of this will have some amount of increased energy. And when this energy is increased, what happens to the equilibrium vapor pressure? It will be shifted to a higher value, right? So this stage will be shifted to a higher value so that the vapor pressure also increases, or the equilibrium vapor pressure stage also increases. So process of vaporization is temperature dependent. That is a known fact for all of us. We keep our clothes for drying outside in the sun for better temperature than inside because the vaporization will be faster. So process of vaporization is temperature dependent. That's why vaporization or the vapor pressure is also temperature dependent. The temperature must be mentioned while reporting vapor pressure, as vapor pressure is dependent on temperature. Now we will see when is the boiling takes place. So boiling can be carried out in an open vessel, and we have taken some amount of liquid in the container which is open. So the container is open. Is there any force which is acting on the surface of liquid now? Yes, it is there. So when we keep an open container, there is atmospheric pressure which is acting upon the liquid which we have kept. Right. So there is atmospheric pressure which is acting upon the liquid in the container. And we start giving temperature to it. So what happens? The kinetic energy of this molecules in the liquid state increases and it started inducing a little bit of vapor pressure upwards. So against atmospheric pressure, some amount of vapor pressure is being induced by the liquid by the help of temperature. So when we keep on increasing the temperature, slowly and slowly, the vapor pressure which is applied by the liquid state increases so as to manage this atmospheric pressure. So initially it will be lesser. So as we increase the temperature and when it reaches the boiling point of this liquid, for example, we can take water. So we are starting the temperature and it is increasing. So initially the vapor pressure will be lesser, and sooner when it reaches 100 degrees Celsius, the temperature reaches the boiling point. The pressure or the vapor pressure applied by the water increases to a level so that to manage the atmospheric pressure. So when the amount of vaporization or vapor pressure is equal to the atmospheric pressure, then the boiling starts. So when the amount of vapor pressure is equal to that of external pressure, then the boiling starts. And one more factor is, in this case, it is not a surface phenomena. The bulk of the liquid or the whole liquid will start boiling. If you have seen this figure, it's not just a surface boiling, right? It is from the down you can see bubbles. From the base level, you can see bubbles coming up. So boiling, unlike the vaporization, it's a bulk phenomenon. Vaporization was carried out just in the surface, and boiling takes place from the bulk. So at a temperature at which vapor pressure of the liquid becomes equal to the external pressure or the atmospheric pressure, vaporization can occur throughout the bulk of the liquid. And vapors expand freely into surroundings, as we told, and this condition of free vaporization throughout the liquid or throughout the bulk is known as boiling. So that is what we explained now. At 1 atm pressure, the boiling temperature is called as the normal boiling point. So if we are considering atmospheric pressure and if we are taking 1 atmospheric pressure, how much is the temperature which is needed for boiling? That temperature is known as the normal boiling point of a liquid. But if we are taking pressure in bar and we are taking 1 bar pressure, then how much ever is the temperature which is needed for boiling is known as the standard boiling point. So one place we are considering atmospheric pressure, another we are considering bar. That's all. And 1 bar pressure is slightly less than 1 atmospheric pressure. So these are two units, and if we consider 1 atmospheric pressure, it is slightly less than 1 bar pressure. It is like millimeter and centimeter. If we consider 1 centimeter is less than that of millimeter, right? So they are two quantities, or they are two units. So if we consider pressure in atmospheric pressure, it will be more than that of if we consider in bar pressure. So 1 atm pressure is more than that of 1 bar pressure, and hence if we consider the normal boiling point and standard boiling point, those also will have a slight difference. The normal boiling point of water is 100 degrees Celsius. So 100 degrees Celsius we get when we consider 1 atmospheric pressure, and 99.6 degrees Celsius is enough to cover up 1 bar pressure. So as we told, 1 atm is slightly more than that of 1 bar. The boiling point also slightly more than when we consider bar pressure. So what is the difference between vaporization versus boiling? Vaporization can be carried out in a closed container, and it's a surface phenomena. Vaporization is carried out just from the surface. The energy of the molecules in the surface will be little bit more, so they escape as vapor. But in case of boiling, it's a bulk phenomenon. It is done from the deep to the surface. All over the boiling takes place, and that is being takes place against the atmospheric pressure, so that we take an open container. At higher altitudes, atmospheric pressure is low. That is a known fact. At higher altitudes, we have experienced lesser pressure. So when the pressure is low, the liquids boil at lower temperatures. Why is that? So we have seen this. So when the atmospheric pressure applied by higher altitude is low, we need, or the liquid needs, just lesser pressure to cover up this. So the temperature needed also will be lesser. So these will start boiling at lower temperature, as it needs just lesser pressure to cover up the lesser pressure applied by the atmosphere. So at higher altitudes, the pressure is lesser. So from the back pressure applied by the liquid can also be lesser at lesser temperature. So they boil early or at lower temperature. In hospitals, surgical instruments are sterilized in autoclaves. So this is an autoclave, so in which the boiling point of water is increased by increasing the pressure above the atmospheric pressure by using a weight covering the vent. So this is a cover which is given for an autoclave. So this cover increases the pressure inside the chamber. So when pressure is increased, they boil at a higher temperature, which we have seen in this case also. So when the pressure is more, the backward pressure which should be applied by the water is also increased. So the boiling temperature increases. So we can clean the surgical instruments at a higher temperature by using autoclave. In case of pressure cooker also, the same theorem applies. We increase the pressure by keeping this lid. So pressure increases, boiling point of liquid increases. So when boiling point, or when the water boils at higher temperature, cooking will be faster. So as it is having good temperature inside than that of boiling point, our food materials will be cooked faster and is very helpful at higher altitudes. So we have seen this in the first slide. So as we increase the temperature inside the container which we contains the liquid, so more and more molecules go to the vapor phase, right? So density of vapor rises. So as we increase the temperature inside the container, the liquid is more and more converted to vapor phase, and the density of vapor rises. So at the same time, the liquid becomes lesser dense. So as it is expanding more, molecules move apart. So when we heat, this liquid becomes lesser dense. When the density of liquid and vapor becomes almost the same, the boundary between this liquid and vapor disappears. So we can't find out where it is actually separating, or we will not be able to find out the boundary between the liquid phase and the vapor phase. So this particular temperature at which the boundaries of liquid phase and vapor phase is disappeared, or we can't make out which one is liquid and which one is the gas. So this temperature is known as the critical temperature. So critical temperature is the temperature at which the boundaries of liquid phase and vapor phase disappear as we increase the temperature. That's all about vapor pressure. And now you can prepare notes by help of your textbook and submit. Thank you.